Alright DB, welcome back. Today's discussion is about chemical equilibrium. If you guys recall, chemical equilibrium is, well, basically almost any chemical reaction that is what we call reversible. So before we start talking, let's define reversible reactions for just a second, in case we kind of forgot that just a little bit. Normally, we think of reactions as being products and reactants oriented. The reactants combine, they react to form products, and then the products are just there. In reality, that's not the case. So let's go ahead and say normally we think that just reactants combine to form products. I'm going to say combine / react to form products. To, oops, little scribble there, form products. So that's kind of what we've been talking about all year, and only a little bit before when we talked about chemical equilibrium did we think of reversible reactions. In reality, another star. So in reality, reactions are reversible. I apologize if you can hear the copier, it's in the next room over and it's really quite loud. So in reality, reactions are reversible. Okay, what this means is that reactants do combine to form products, but products also combine to form reactants. So let's try our best to write that. Reactants do combine, or reactants do form or produce products, but some products do come back and they form reactants. But some products do form / produce. That word is produce, by the way. Reactants. Alright, so I'll give you guys just a second to do that while we write an example. And I think my example today is going to be the reaction of carbonic acid in soda. It's also the same reaction that happens in various places in your body. But we're going to use our soda example just for the moment because some people can be a little bit weary of blood. No worries. Okay, so here's carbonic acid in soda. Soda is made mostly of water. Mostly water. The way soda is carbonated, or the way soda is, made to have that fizzy, bubbly goodness, is that it's pressurized with carbon dioxide. Carbon dioxide is produced by you when you breathe out. It's also produced by car exhaust and a number of other things. Now we can definitely hear the copy machine. All right, so ordinarily we think of these things as the reactants, because they are. They're on the left side of the equation. They react together, and then equilibrium happens. So this arrow ordinarily means that, these are the reactants, they're gonna go and they're gonna form products. The product, usually in this case, is gonna be full-blown carbonic acid, or H2CO3. All right, so here are our products. They are the things produced in the reaction. Simple, easy peasy. Ordinarily, this is what happens. The carbonation of soda is actually a little bit more complicated than that. But before we talk about that, let's really focus on our equation. Our equation is saying if we were to turn it into words, water, which is the H2O, reacts with CO2 to produce H2CO3, which is also called carbonic acid. Okay, so that's kind of the reaction we're used to. It's reversible though. It can go back the other way if we follow this other arrow to the left. The H2CO3 which has a name, the name is carbonic acid, breaks down and it produces carbon dioxide and water. Oops, made a little mark there. So two things happen. Initially, you have water and carbon dioxide forced together under high pressure. They produce carbonic acid, and then sometimes the carbonic acid breaks down and it produces carbon dioxide and water. When does it happen? When do you see carbon dioxide, which is a gas, by the way, being produced? Well, you see that when you open the soda. Why does that happen? Why is there no carbon dioxide present inside the soda before you open it? That's kind of the topic of equilibrium for today. So, let's give another example here. Actually, we're going to keep this example going. We're going to talk about several things that affect chemical equilibrium. It's going to sound an awful lot like the same things that affect reaction rates, because they are kind of the same things that affect reaction rates. Temperature plays a big role in what direction the equilibrium is going to shift. You can actually affect how many products are going to be formed, how many reactants are going to be formed. You can shift the reaction either direction. That's a principle we'll talk about in just a second. Temperature plays a big role. Pressure plays a big role. And molarity also plays a big role. Molarity, which is also the same thing as concentration. So those are the three things that have a huge effect on molarity or concentration. I'm sorry, on what direction the reaction is going to shift. We're going to talk about temperature first. So I'm going to rewrite our reaction because I'm out of room on the other paper. So H2CO3. And I'm going to add something else on the right side of this reaction. So you should consider rewriting it on your own if you guys are taking notes, because it's actually a tiny bit different. When you pressurize these things, I'm going to say that heat could be produced as a result of pressurizing all this stuff. I don't actually know that for a fact. This is just for the sake of example. The stuff on the left side are still the reactants. So they are still the reactants. The stuff on the right side, still the products, except we have an extra product. One of the products of this reaction is heat. Let's talk about temperature's impact on this stuff. So there's something called Le Chatelier's principle. And let me see if I can actually write this real quick. Le Chatelier's principle. Principle, not principal. All right, so Le Chatelier's principle is that you can adjust anything in this chemical reaction, the concentration of the water, the amount of heat, and when you do affect whatever's in the reaction, you'll shift the reaction to the right or to the left. If we look at heat, thank you. Oh, you made them all, thank you. If you look at heat, if we heat up the reaction, if we add more heat on this side, actually, you know what? Let's ignore temperature for just a second. Let's just talk about Le Chatelier's principle. And then we can go back and talk about temperature. Le Chatelier's principle basically says that if you increase something on one side of the reaction, it's going to shift the reaction in the other direction. So if you increase it could be temperature, pressure, or concentration / molarity, of something. It could be a product or a reactant, of a product or reactant, a or reactant, you will shift the equilibrium of that reaction. All right, good. So Le Chatelier's principle, if you increase the temperature, pressure, or concentration of a product or reactant, you will shift the equilibrium of that reaction. So now I think we can talk about temperature just a little bit. Now that we kind of have a nice definition for Le Chatelier's principle. So I'm going to rewrite the equation once again, my mistake. All right. So we have water plus carbon dioxide producing H2CO3 and heat. I would still label these as reactants. React. And products. Still would label these things. Okay. So if you haven't, do so. It is super duper important. A little sip of water. Okay. Let's talk about what effect changing temperature would have on this reaction. So we see heat on the right side as a product of this reaction. Le Chatelier's principle says if you increase something on the one side of the reaction, it will shift the reaction the other way. What that means is that if I increase the heat produced on this side of the reaction, it's going to make the products form reactants. If I decrease the heat, if this gets really small, the reactants are going to want to form products. So whatever you do to one side, if you increase something on this side, whether it's heat, temperature, which is heat and temperature, same sort of thing. Not exactly the same thing, but very closely related. If you increase the heat, the pressure or molarity of anything on this side, it's going to force the reaction the other direction, meaning more and more reactants are going to be produced. On the reactant side, if we increase the concentration or the pressure of the water or the CO2, it's going to force products to be produced. So in this case, heat is on the right side. If we increase heat, more reactants are going to be produced. More reactants will be produced. That's because, oops, sorry about that. The things on the product side are going to get really congested. Not really congested, they're going to get really tightly packed. They're going to start reacting more and more because there's more of them. In this case, there's more heat. And, you know, heat is a product. Heat doesn't like to exist at the same time as this thing, so to speak. And it's going to force the reaction the other direction. If we decrease the temperature, what do you think would happen? So if you decrease the heat produced, if you cool down that reaction, do you think more, here's heat, if it goes down, heat gets less and less, are more products going to be produced or less? I am going to say more products will be produced. Will be produced. All right, so that is an application of Le Chatelier's principle. Let's use a firm application of Le Chatelier's principle with respect to actually pressurizing and carbonating soda or any sort of bubbly beverage. So once again, I shall write the reaction. H2O and water, carbon dioxide, and pressure. So, and pressure. This time they're just going to make the carbonic acid that gives soda a little bit of a sour taste, that makes soda fizz, that gives soda or carbonated water the taste that it does. All right? So what effect is pressure going to have? In reality, when you have CO2 and water in the same place at the same time and you pressurize it, so you force all that CO2 into the water with a lot of pressure, you're going to make lots and lots and lots and lots of H2CO3. It's pressure. That is because of what we talked about on the last page, Le Chatelier's principle. If you do something to this side of the reaction, if you affect one of the reactants, it's going to make the reactants react. It's going to make them form products. So, in reality, lots of pressure and CO2 and water will make lots of carbonic acid. Before you open a soda, the pressure on the inside is really, really, really high. What happens when you open the soda? The pressure inside gets really, 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 really low compared to where it was. So if this pressure goes way down, the products are going to want to form more reactants. So you're going to get tons and tons of carbon dioxide gas. So what's the effect of pressure on this reaction? If pressure goes up, more carbonic acid will be produced. So that's how you make soda. That's how you jam all that gas into the soda. If you ever look at a soda through a clear bottle that has not been opened, there's a tremendous amount of gas trapped inside the solution in the form of carbonic acid, and that's kind of odd to think about. If you decrease the pressure, when you open that soda, what's going to happen? So this is going to go down. The reaction is going to shift in that direction, so it's going to shift to the left more. So when pressure goes down, more reactants will be produced. Let's talk about molarity and concentration on the same page since we can. We have the space. If you decrease the concentration or molarity of any of these things, any of the products or reactants, it's going to shift the reaction in whatever direction. So let's say we increase the concentration of CO2. So we're going to increase the concentration of CO2. It's going to shift the reaction to the right, forming more products. The reaction will shift right. Ooh, random cursive. Forming more products. And the opposite is also true. If you decrease the concentration of CO2, the reaction will go the other way. Let's talk about decreasing the concentration of the H2CO3, just as a slightly different example. So we're going to decrease the concentration of our carbonic acid. All right, what do you think is going to happen? I'll give you a second to think about it. All right, that was more than a second. You're decreasing the concentration here, so the reaction is going to shift in the direction that something is decreasing. All right, so let's write that now. So we decrease the concentration of the H2CO3, the reaction will shift in that direction. Go. I think it's all on the screen. Perfect. Wonderful. Fabulous. we do need to talk a tiny bit about the effect catalysts have on equilibrium. Let me prepare that page. What effect do catalysts have on equilibrium? They don't have any effect on equilibrium. None at all. None at all. So perfect, wonderful, absolutely fantastic. We should actually define chemical equilibrium. Perhaps this would have been helpful at the start. Yeah, let's go ahead and define equilibrium in the last minute and a half of this video, just in case we kind of forgot. So normally we think of a chemical reaction as just something that starts and then ends, but it does not. Chemical equilibrium is when chemical equilibrium, you can hear me sounding out the words, is when the rate, so last time we talked about reaction rates, the rate of product and reactant formation is the same. That's what it is. So chemical equilibrium is when the rate of product and reactant formation is the same. It's not when the reaction is over. People get that confused all the time. Chemical equilibrium is not when the reaction is over. Write that down. My little timer on my video thing is going to run out before I have a chance to write that on my paper, but you should write on your paper, equilibrium is not when the reaction is over. Reactions never end, ever. Well, some do. Equilibrium reactions do not end, I should say that, because that's true. All right, so I hope you found this video helpful. I hope it was a good refresher on chemical equilibrium. This is all that we are going to have to know. We do not have to know how to write equilibrium expressions, which are those large complicated things with K, E, Q. Thank you. Have a good day.